Hello class, in this module we will be focusing on quantum numbers. We just got finished going over all the orbital shapes, and now we're going to focus on the quantum numbers just to wrap everything up. This chapter, especially the end of this chapter, is pretty abstract, so I want to go over this again. So here, let's refresh our memory. We have our principal quantum number. So that's our shell, right? So that's our shell. Now that is our n. Our n, I call it the shell. Also you'll see terms like principal energy level. So these are all the same terminology for the same thing. So what does n represent? It represents the size, and I think you guys have gotten that when we talked about the 1s, 2s, and 3s as n increased, the s orbitals increased. So it's the size and the energy of the orbital. So values of n are, again, counting numbers, and when n equals 1, it's called the ground state. So over here, n equals 1 is the ground state. Now notice on this plot we have energy increasing in this direction, and notice what happens to our n's, or our principal energy levels, or our shells. As we get higher in energy, the energy gap decreases. Okay, so here the energy gap gets smaller. Now we can figure out our energy of each of our principal energy levels through the equation Em equals minus RH, and hopefully you recognize that as the Rydberg constant, over our quantum number n, principal quantum number n. And again, RH is going to equal 2.179 times 10 to the negative 18 joules. Okay, so we can actually get, we could before as well, but we get energy, the energies for our different energy levels here through that formula. So that is our n, our principal quantum number, n, or the principal energy level. Okay. Now the second quantum number, so remember there's 4 quantum numbers. The second was our angular momentum, or L. And this is also known as your subshell or your sublevel. So this again specifies the shape of your orbital. And we've went over this several times, but hopefully it'll make more and more sense. So if we have our n is 1, so here our n is 1, our n is 2, our n is 3, and our n is 4, so that's what these represent. Then our L's will be the shape. So here's our S, and then in n equals 2 we can have an S and a P. But before I explain that, each value of L has these integers. So S would be 0, so these are our L's, 0, 1, 2, 3, which would be our S, P, D, and F. So we've seen that several times. And what we want to notice that is if we have n equals 2 here, we know we could have 2 sublevels or 2 subshells, S and P. And if we have an n equals 3, we've got 3, S, P, and D. And if n equals 4, we have S, P, D, and F. Okay, so with those, our n equals the amount of sublevels that we have. Now that is our, again, our angular momentum, so our shape. Now let's move on to our magnetic quantum numbers. So this determines the number of orbitals and orientations in each sublevel. Each value of m sub L, again, has that specific orientation, and I showed you that with the orbitals. And we went over how to calculate m sub L. So it's, you go from minus L through 0 to plus L. So for S, it would just be 0. You can't have any more than that. P has 3, minus 1, 0, 1, and again, that should make sense. It has 3 orbitals. S has only 1 orbital, that's why it's 0. D, if we start minus L to plus L, minus 2, minus 1, 0, 1, 2, should make sense because we only have 5 orbitals. And then F should have 7. So 1, 3, 5, and 7. Okay, and that's what we are shown here. So n equals 1, n equals 2, n equals 3, and n equals 4. So an n equals 1 shell only has an s orbital, and n equals 2 has an s and a p. But how many total orbitals? Well, because p has 3, you have 4 orbitals total. And at n equals 3, you have a sublevel of s, p, and d. S has 1 orbital, p has 3 orbitals, d has 5. So total, you have 9. And I hope this is making sense now. And finally, the last quantum number, which we haven't spoken about at all, is m sub s. This is the spin or the orientation of an electron. There are only 2 possible orientations. Spin up. So when we were drawing orbital diagrams in your intro class, we would usually draw a line and we would put one electron having a spin up. And if we filled that orbital, we would show a spin down. We'll talk more about what this means in the next chapter, or with the orbital diagrams. But here we assign values to these. And our MS's have to be a plus half. And over here for down, it didn't show it, but this should be a minus half. So going up, this would be plus half if we were to have our m sub s, and this pointing down arrow would be minus half. They would have to have opposite spins. Okay, now I want to put all of this together with our quantum numbers, and I like to use the periodic table to do this, just like when I do electron configurations. So your periodic table will reflect the quantum mechanical structure of the atom. And each element's location reflects the quantum numbers of the last orbital that is being filled. So let's go over this. So we know that n equals 1 starts here from when we did electron configuration. So here n equals 1 will be at the top. And as we go down, it goes 1, 2, 3, 4, 5, 6, 7. Now where it starts to change with our n's are in the green block here. We know that the n for this block, L equals 2, this will start at 3. This starts at 4. This is 5. And this is 6. Okay. And then over here, we know that this starts at 4. And then this starts at 5. So what we have to imagine here is that this region that's in orange, this will be L equals 0. What is L equals 0? That is, we can use our symbol S for that block. So this orange portion is our S block. And notice over here with helium, that really belongs to our S block. Now, that means that for helium, it's going to be in the n equals 1. Okay, it will only have n equals 1, L equals 0. So if that's n equals 1, L equals 0, so that is an S, it'll have only an S orbital. Now L equals 1, we know that means P. So everything in blue here is going to be our P block. So this is our P block. And then our L equals 2 is our D block. L equals 3 is our F block. Okay, so we're going to use this to figure out different types of questions or go through different examples. Okay, so the periods are the ones that go across again. So the periods, those are going to indicate the value of our principal quantum number for the valence shell. Okay, so we're going to use that for our valence shell. And our lanthanides and actinides, they are in period 6 and 7, but when we do quantum numbers, we're not going to use 6 and 7. So recall, we're going to use 4 and 5, just like in electron configuration, 4 and 5. The block, this indicates the value of our angular momentum for the last subshell or sublevel. Okay. When we build up in electron configuration. And blocks, again, they are named for our subshells or our sublevels. And again, those are S, P, D, and F. Each block contains a number of columns. And those are going to be equal to the number of electrons. They're equal to the number of electrons that can occupy that subshell. For example, the S block in orange, it has 2 columns because there's a maximum of 2 electrons that occupy any orbital in an S subshell. Recall that an orbital can only have a maximum of 2 electrons, right? Now our P block has 6 columns because there is a maximum of 6 electrons. So let's go back to this picture so I could show you. So S has a maximum of 1, 2, so it can only hold 2 electrons. P can have 1, 2, 3, 4, 5, 6. So there are 6 columns, so 6 electrons. So 6 columns, 6 electrons. Now in green, these are our Ds. Now our D has how many columns? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has, so the D block has 10 columns, so it has a maximum of 10 electrons that can occupy the 5 orbitals in a D subshell. And finally, the F block, let's go back up to the F block. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns. Now it has 14 columns because there's a maximum of 14 electrons that can occupy these 7 orbitals. Okay, so if we think about the electrons, so all of these different columns represent the electrons. So S then can have 1, 2, P can have 6, because there are 3 orbitals, right? S has 1 orbital. S's always just have 1 orbital. So if we've got 10 electrons, how many orbitals? Well, it has 5 orbitals. So you just multiply by 2 to figure out how many electrons. Over here, we've got 14 electrons. So how many orbitals would that be? It would have to be 7 orbitals. Okay, I hope that makes sense. So now, again, this is pretty abstract. How would we use this? Let's go through some examples. Now, what value of L is represented by an F orbital? So if we look back at our L's, we know from before that an F block has to have an L equals 3. So our L equals 3 comes from the table that I was making. So if our L is 0, 1, let's make this straight, 2, 3, we know this is S, this is P, this is D, this is F. So L would have to be 3. Okay. Make this box a little bigger. I'm trying to make this a little smaller. Now, what values of angular momentum L and m sub L are allowed in the principal quantum number 3? Okay, so what I'm going to do here is stop the module, and I'm going to make one more to go through the rest of these problems because I'm running out of time with this video. And then we'll go ahead and look at a few more examples so it makes sense how to solve these types of problems. Again, it's seemingly abstract, but once you do the examples, it's not so bad. Okay.